we had done this program wherein we had accepted three numbers from the user, displayed them, and also found the sum of them, right? Okay. If I tell you, see, in your data structures, you might have observed there is a chapter by the name searching. Have you done that? Binary search, linear. You've done that. So, did you understand the search? Okay, then let's try to take that topic because that will be based on array concept. So, search is of two types, linear and binary. Fibonacci search, I'll have to check what it is. So, let's first discuss these. Yeah, let's consider these two, and also I'll research for the Fibonacci search, and then I'll update you on that. Okay, so we have linear search and we have binary search. So, we have linear search and we have binary search. So, linear search is very slow. Binary search is fast, very fast. Linear search is suitable for small data. Suitable for small data set. And binary search is suitable for large data sets. So if the data set is large in number, then you can use binary search. In linear search, data need not be sorted. Sorted, not compulsory. But if you are trying to do binary search, data must be sorted. Else, binary search will not work. And linear search works in the time complexity of O of n. Have you gone through this time complexities? You understand what is O of n? So like what? O of log n. Okay, and this uses the algorithm. Yeah, yeah. Okay. Yeah, yeah. Yeah, you there? Yeah. So this is what is the primary difference between these two types of searching. Okay. So now what happens in linear search is in linear search we search for the data at every position. Okay, it's like a policeman has, you know, these are the five criminals, and the policemen have lined them up in the police station, and the accused or the victim has been brought to identify the criminal. So he will first go and check over here whether he is the criminal. Then he will go and check over here, then over here, then over here, then over here. And if he finds anyone, he will stop over there. The searching will stop, correct? Is the same as, let's say you have 5 drawers in your living room, and you have a habit of coming and placing your keys in any of the drawers. Okay? So you have that habit that whenever, one second, huh? So you have a habit of placing the key in any of the drawers randomly, okay? So now, and let's say someone stays on the 4th floor of the building and there is no electricity today, so the lift is not operating, and that person has now gone down and is in the parking. Now he's too lazy to climb the first story, so from the parking only he's shouting and asking his mom, talking to his mom from the window and telling, please check in the drawers, I forgot my bike keys. So the mom checks in the first drawer. Does she find the key? Second drawer, did she find the key? Third drawer, does she find the key? And then she will throw the key to him. Will she search in the fifth and fourth and fifth drawer? No, right? So the search will stop over here, right? Once we get the key, we'll stop the search. Okay, second scenario. When she searches in the first drawer, does she find the key? So will she say, son, the key is not there? Will she tell his son that the key is not there? Yeah, so when will she say not found? So when she has searched the last drawer and then she has not found the keys, that time she will tell not found, right? So just by looking at the first drawer, she will not conclude not found. So this is the day-to-day usage and examples of linear search. So why I called it slow is, now there were 5 drawers, so it was suitable that I could use linear search over here. What if there are 500 drawers? Now opening each drawer and checking, that will be too slow, right? Hello? You there, Aryan? What if there were 500 drawers? Then it will be too slow, right? It will be too slow, right? Okay, so this logic will fail. Let's say after 12th standard, people have applied for their engineering entrance exam, right? You all have called MHCET. So, and the university has put a list of all the candidates who have applied with their percentage in alphabetical order of their names. So all the surnames with A have come for, they have put a list with all the surnames of A's, then all the surname of B, all the surname of C, and all the surname of C, like this they have put, okay? And there were 5,000 applicants. There were 5,000 applicants who had applied. Now, if there is a person whose name is, let's say, Sharma, and he wants to look for his uh, score, will he start looking from A, B, C, D, E? So there he will not use linear search. He will not come from the start. Then there randomly he will open, randomly he will go and check one mark, and he sees over there it is written Jadhav. So where does he have to go? Left or right? Right. Then randomly he goes and see the next page. There it is written, let's say, with any T surname, Thakur. Now where does he have to go? Right. Then here, then he goes left. He sees Saha. Now, and then go towards further right. Goes SANSH. Right. So after every check, he's coming closer. After every check, he's coming very closer to his name. Right. We'll use binary search. Here what will we use? So we will shift from left to right depending on the data. Okay. So let's first start with linear search and see how it works. So I take an array of size 5. I'm sharing my this turbo. See, you can see that, right? And we will take the number which we want to search. So first we'll accept the 5 numbers from the user, and once the user enters the 5 numbers, we'll display the 5 numbers, and then we will ask the user to enter the number he or she which wishes to search. So we'll say printf /n, please enter number to search, and scanf %d comma and n. You have to declare n. Yeah, we declare n. Now I want to search whether the n exists. So if I enter the 5 numbers as 10, okay, any random numbers, okay, 18, 45, 1, 63, okay, and 27. In random order I can enter. Now the number I want to search is 63. Is it there? So what will I do? I start from the 0th index, and what will I check? If the number there at which position? I, right? This is what we are checking. If the number is there at any of the ith position, what will we say? Found, right? And then if it is found, search further. Then what will we do? Will I put a else over here and say not found? Will I put a else over here and say not found? Yeah. So now if the number I have found at any position, so now what is the value of I in the first iteration? I is 0. So is the, okay, here. So I is 0. So what is AR of I? 18, right? So what are we searching is 63 equal to 18, true or false? It will not go in if. Then for I increment I becomes 1, is 63 equal to false. Then I increments to 2, is 63 equal to 1, no, I becomes 3, is 63 equal to 63, found, and you will break the loop, right? So when will we say not found? Should I put a else over here and say not found? No, else will not be over here. Else is not over here. Why? Because this else it will go when the first 18. So 63 equal to 18. True or false? So will you say not found straight away? You will. When will you say not found? When will the mother say not found? Rows have been searched, right? So now we are only saying after searching for the first one. So else will not be there, because if it is else, the output will be not found, not found, not found, found. Getting it? So do you want the output to be in this shape? Times not found and then once found. So when will you say not found? Yeah. So now where will we say not found? It will be outside the loop. Yeah, so no, I'm asking where will we print that in the code? Inside the loop? No, we will not put inside the loop. See, if I am searching for 36, right? So 36 with, so what is the value of I? 0. So 36, 60, 30, 36 equal to 18. True or false? False. Then it will not go in if the 4 increments I becomes 1. And now 36 equal to 45, again false. Again it will not go in this. Then again I increments to 2. 36 equal to 1. Again false. I becomes 3. 36 equal to 63. Again becomes false. I becomes 4. 36 equal to 27. Again becomes false. I becomes 5. Is 5 less than 5? Is 5 less than 5? So loop will terminate, right? So if my I is reaching 5 means it is, because if it is found, it is breaking. If it is found, the loop is breaking midway, right? If I was searching for 1, if I was searching for 1, what time will the loop will break at index 2? Yes or no? Because 1 it has, so the loop will break at 2. Now my loop has come till 5. What does this suggest? Yes, outside the for loop put a if, that if your I is equal to 5, then you can say printf not found. Getting it? When to say not found, we will not say not found inside the loop and your main closes. Let's try to run this code. Okay, there is, we haven't we declared I? We didn't declare I. Okay, now let's enter the numbers, this order. 18. You can give us space also to enter numbers, okay? 18, 45, 1, 63 and 27. Okay, numbers. Now I am searching for 1. What will it tell? Found. Is it saying not found again? No, right? If I search for 36 then, so if I have 18, 45, 1, 63, 27, and if I say 36, it will say not found, right? Okay, any other logic you can apply over here? Can you apply flag logic over here? You tell me. Flag, we wait for a condition to occur, right? Once the condition occurs, set the flag. So we will keep on searching the number. Once I find the number, I'll set the flag. Simple logic. See, I'll take a flag, initialize it to 0. Okay. So by default, I am assuming it is not found. Assuming what? When I find, I'll make the flag 1, right? So when I find, what do I make? The flag 1 and we break it, right? Now flag 1 means what? Flag 1 indicates, flag 1 indicates what? Found. So if the flag is 0 till the end, means not found. So over here, see here, if we are searching for 63, okay? So I becomes a 0. So what are we searching? 63. And the flag is also 0, right? Flag is also 0. 0 means not found. Okay. So now what are we searching? 60. We are searching for 36, right? Let's have 63. 63. So now is 63 equal to 18? No, right? Then it will not go in the if, and then 63, then I becomes 1, then 8, 63 equal to 45. No, I becomes 2, flag remains 0, 63 equal to 1, not found, flag remains 0, 63 equal to 63. Now we will display found and we set the flag to, so flag 1 means found, and then we will break the loop, and now will come outside is the flag 0. So it will not display not found. If the flag remains 0 from start to end means not found. So now let's try to run this code. Enter the 5 numbers: 18, 45, 1, 63, 27. And now I'm searching for 45. It will display me what? So like this you can play with the flag variable also. So you will, the purpose of the flag is you wait for a condition. Once that condition is achieved, you set the flag, and then you check the value of the flag outside, whatever you are looking for. Understood? So this is called linear search. Now let's go to binary search. Binary search is very interesting. Binary search, what happens that let's take this example. I give you the example, right? That you are searching for that roll number. Okay, so this is the A to Z. All the, you see my screen, paint screen. Okay, so all the percentages are put up A to Z, correct? So now once that person comes in, he comes in and checks at which position? J, right? So he is looking for Sharma. What is he looking for? Okay. So let's say Rajat Sharma he is looking for. Sharma Rajat. And now as he comes in, he first sees that in front of him he has the list. So he sees over there, he sees J over there. He sees Jadav's surname over there. So now where will he go to? So in one glance he will conclude that this area is not for me. This area I can eliminate. Okay, so in one glance he has eliminated this. So now he will search from where? Jadav to Z, right? So now his search has, okay, then he goes and checks for what? Thakur, right? Then he goes and check for Thakur. Then what will he say? Thakur. And where is his name? Left or right? So in one glance he will say this area also is not for me. So now where is my search area? Jadhav to Thakur, right? And then he goes and checks for Saha. Now this area also is not, now he's eliminating the area, right? He's reducing the area of search. And now then he sees uh, Sharma and Kit. What does he see? Now, yes, so now this area also eliminated now. Okay. Then he sees, okay, Sharma and Suraj. Now, SUNRA, right? So now every search he is doing is reducing the area of his search now. Now you Sharma Ankit and Sharma Suraj, and then he will gradually see Sharma Rajat, right? So this is faster, right? This logic is faster. What if you would have done? What would I if you would have browsed the entire A's, then entire B's, and then entire C's? If you would have done linear search over here, would have taken a long time to search for his name. With binary search, it has become faster. But what was the prerequisite? The mark sheet would have been put up alphabetical order, right? What if the mark sheet were put up based on the percentage from big to low? What if they put the percentage wise mark sheet, that 99.9 percentile ones, then 99.81, then 99.71? Now does he know where he lands up? So here it was not possible to do binary search. Then here you do linear search. Check for each number, each list, right? How we do it in practical world? Let's say I have a array. We'll take the same array which we have, and it has 5 numbers, right? So what are the indexes of that array? Indexes are 0 to 4. Okay, so I'll mark them as red. So now it is prerequisite that this array must be sorted, else the binary search will not work if it is not sorted. Okay, so now if I enter 1, 18, 27, so I have to sort that data first. 45 and 63, correct? So whatever input I am doing for linear search, I can't give that same input over here. I'll have to sort it first. Okay, so the black is the indexes, and the red is the indexes, and the black is the data. Making sense to you? Okay, so now going by the indexes, what is my total area of search? What is my total area of search? My start, I'm searching from between 0 and 4 index. I'm searching I'm searching between which two indexes? I'm searching between 0 index and 4 index. So this becomes my beginning and this becomes my ending. Okay, I'll try to color code it for you. And the ending can also be size of the array. The ending can also be the size of the array, but just for the sake of the discussion, we'll take first index and last index. First index and so I will call this as the first. So my searching is between the first and the last. My search is between the last. Okay. Okay. So till my first is less than equal to last, my loop will run. So what is the value of my first over here? And what is the value of my last? So the loop will run till when? Till the first is first is less than or equal to last. Okay, so this is the father, okay, and this is the son. So when will the father go and shop for the son on his birthday and buy dresses for him and buy shoes for him? Till the son's height is less than the father's height. The moment the son grows up and he touches his father's height, that time the father should give all this to the son, that you buy clothes and you buy shoe for yourself, now you're big enough, right? The loop will run till the first is what? Last. Once the first becomes greater than last, the loop will terminate. Okay? If your first overtakes your last, that is the time when you will say not found. What will you say? So there is a chances of being found till when? Till when is the chances of the number being found? When the last. Once the first becomes greater than last, there is no chance of the number to be found. So directly you will say what? You will come out of the loop and you will say, if your first is greater than last, you will say not found. Understood this logic? So is the logic of not found understood simple? Now, okay, now let's focus on the logic of the found. So you will initialize two variables by what values? Your first is equal to the first is equal to the first index and last is equal to the last index. So in between your loop will run now. So now what you have to do is we will search at the mid. Where will we search at? Which position will we search at? We will search at the like how we went to search for Jadav, the first one, right? So directly now we will search for the mid position. So what is the mid then? Calculate the mid. Is this the right formula? Is this the last? Is this the right formula? No. By rule of board mass, it will do the last by 2 and add it to first. Yes, you'll add the bracket in the numerator that you first solve this. Okay, so by virtue of this, what is the mid now? By virtue of this, what is the mid? Now by this calculation, what is the mid? What is the value of the mid? So your mid is over here, correct? This is where your mid has come. So now first thing first, search at the mid. Search at the mid. So what are we searching for? Let's say we are searching for 45. What are we searching for? So that is an n, right? So you will say if n is equal to where mid is 2. We are, we are searching for the index or searching for the numbers? Are we searching in 1, 18, 27, 45, 63 or are we searching in 0, 1, 2, 3, 4? No, are we searching for the indexes or are we searching for the values? So will you search n equals to I or ARR of I? Are we searching for in 1, 18, 27, 45, 63 or are we searching for the indexes? That is index 2 present or index 3 present? I is, you are searching for 2 then. You are comparing 45 with 2. My question is, we are looking for 45. We are looking 45 in the indexes or what? Or are we looking at the values? So will it be I or ARR of I? Right. So will is n equal to ARR of I, right? So ARR of mid, ARR of mid. What is the value of mid? What is the value of mid? Mid is 2. Mid value of mid. See, there are two things. Mid and ARR of mid. Mid and ARR of mid are two different things, right? So what? Yeah, Aryan, you there? So my question is, you will search for ARR of mid, right? So n means 45. Is 45 equal to what then? So the first iteration you're checking is 45 equal to, so true or false. So your name was not found at Jadav. So now where will we check? Left and right, right? Yeah, when you go to right. Okay, so first if it was found, I would have printed found. If you were searching for 27, would have found. If we were searching for 27, we would have printed found, right? And then no need to search further. Yeah. Okay. Now if it is not there at 27, I will check whether it is, whether the number I am searching for, if it is greater than error of mid, then no, no, then what will move? Then what will be a search area? Then what will be a search area then? So if your search is towards the right hand side, then your first will come to mid plus one. What will your first move to? And if you're neither equal nor greater, when it is lesser, so in else your last will go to mid minus one. Mid minus one. Last will be equal to mid minus one, right? So this all will be inside over here in the loop part here. Getting? So this is your, so now in the first iteration was 45 and mid you got 27. True or false? False. Then is your n, means is your 45 greater than 27? True or false? True, right? So what will happen? First will come to where? Your first will come to where? So first will come here. Getting? And now as it is if, else if and else, so it will go in either of them. The loop. Yes, sir. So if it goes into else if, it will not go in else. The loop completes, and then again is your first is 3 less than equal to 4. Yeah. So again comes and then do what? Is 3 less than equal to 4? Yes. So again calculate the mid. What is the mid now? 3 plus 4 divided by 2. But it is an integer. All these three are integer values. So what is mid now? So mid will also come over here. And now what is the n of searching for 45? Is 45 equal to 45? The loop will say found and you break, right? And did your first cross the last? Did the first cross the last? No, we did it cross. But after the loop we will check this also, no? After the loop we are checking is first greater than last, is 3 greater than 4. So it will not display dot form. It will not go in this, right? So now if we try to run this code, and okay, so we can't take the same data set. You want this code or linear search? Then let me share it across with you. Okay, so now I'll just modify this code and will accommodate binary search for you over here. You can see the screen, right? So I'll just not waste my time in taking the numbers. We'll just hard code the numbers. Numbers, you know how to take except now. So we'll have 1, 18, 40, 27, 45, 63, correct? No need for a flag over here. What do we need over here now? First, are you able to see my screen? And we require 3 variables, first, last and mid. First initialized to 0, last initialized to 4. And then what will be the loop? While your first is less than or equal to last, do what? Yeah. While your first is less than or equal to last, the loop will continue. And if your first overtakes your last, you will say what? Not found, right? Now what to do inside? First calculate the mid. What will be the mid formula? Divide the whole divide by 2. And then what will you check? If the number I am searching for, okay, we'll take that number we are searching for. So let me copy it from the notepad. So directly I can paste this and the number to search, and we're taking it n, and let's declare n also. Okay. I'm doing it on separate line, you can do it on one line also. You can declare all this on one line also. So n. So now we have got n. So n, let's say, is 45. So what are we telling? If the number I am searching for, I get it at which position? Yeah, or mid. Then what will I say? And will I search further? Break, right? Once I find, I will break it. Okay, if not greater, not equal, then I will check whether it is greater. So what if your n is greater than error of mid? Means the number is towards the right of mid. So to the right of mid means you move the first to the right of mid, right? So first goes to where? To the right of mid. If it is neither equal nor greater, then it is lesser. In this case, what happens? Your last goes to the mid minus 1. Correct? These two brackets can be eliminated to make the code more. Yeah, we can do without these two because we have only one line, right? And now after the loop, I will check if the first and the last not found. Let's run the code. Which number you want to search in this? Found, right? Okay. If you want to display found at position, what position is it found at? Index or position? which index or position 3. So which position? Fourth. How will you display that? Found at position 4. How will you display that? Found at position 4. Is it? What happened to you today, Aryan? See, here your indexes you should know, right? That these are my indexes. So you have indexes 0, 1, 2, 3, and 4. So when we found 45, at what index did we find it? Who was pointing to 3? Mid. You're always looking at mid, right? So you will display mid plus 1. Mid is pointing to this 45, no? 3 is the mid. So you will, now if I say 45, what are index 4? Okay. And if I search for 77, is it there? So, no. And when I say not found, and if I display the first and the last, what will be greater? I would display the first and the last, which would be greater in not found. Yes. So if I display the first and last, you'll always see that the first is greater than the last. See. Now let's run search for 89. Is 89 there? So what is the value of first? And last is 4. And whenever you will find, at that time you will see that first is less than last, always. So if I run this code, search for 45. First is 3 and the last, right? When we had done over here, remember? 45 we had searched. The first is 3 and last is 4. Okay. You've told me that you know about the time complexities. So what is the time complexity of this algorithm? Yeah. O of log n, remember? So are you familiar with these terms? O of log n, O of n? Asymptotic notations they are called. So why is it O of log n for binary search? Do you have any idea? See, log, now I want you to tell me what is log 100 to the base 2. Yeah. What is the output? What is the answer of this? So the calculation of this is very simple. The calculation is very simple for this. What you have to take is, you take what you are finding for you. You are finding for which log 100, right? And for what base? So you keep on dividing that number with 2 till you get 1. So how many attempts do you require? So first attempt will give you 50, right? Then again divided by 2 will give you 25. Then again divided by 2 will give you 12. Yeah, remove the 0.5 aside. Okay, keep the 0.5 aside. Okay, we'll use that later on. And then 12, you just round figure it 12. Then divide that by 2. How much will you get? 6. And then divide that by 2. 3. And divide that by 2. Okay, so you just keep that 1 over here and the 0.5 carry forward over here. Okay, so how many divisions did it take for me to reach from 100 to 1? So the answer will be log 100 to the base 2 will be 6.4 or 5, because we have not considered these two values, no? So maybe it will be 6.4. Getting it? You got it? Now what would be log 100 to the base 10? 2, right? Because if I divide 100 by, if I recursively divide 100 by 10, how many attempts will it take to reach 1? 2 attempts. So log 100 to the base 10 is 2. The answer? So why we call this in the time of log n is because to search for any number. So if your array was of size 100, if your array was of size, the last index would have been, so if I would search in this array, max to max, how many comparisons would I make? I would make max to max 6.4 comparisons and I would get the number. And if I would use linear search, the time complexity is O of n. So if the array is of size 100, I would make 100 comparisons. Search at index 0, search at index 1, search at 2, search at 3, keep on searching till 99, max to max. That is the upper bound. O, big O gives the. So here if I am searching for any number max to max, I will make log of that size to the base 2. So what was the size earlier we had? We had size 5, right? So the answer would always be in this. So how many attempts does it take from 5 to reach 1? 5 to the base 2 will give me 2.5. So let's keep the 2, carry forward the 0.5, and then again 2. Okay, so let's, if it is, let's say 2.9 also, let's say 3 max to max. So your answer of your binary search will always be, if the size is 5, it will always be in 3 attempts. It will always be in not more than that. So if I take the integer iteration counter, okay, as we do last time around, and for every while I am incrementing the iteration counter, and then I will display found at position this in percentage d iterations, and that is showing IC. Okay, this value of IC will never increase more than 3. Will always be, because the size of the array is 5, right? And log 2 to the log 5 to the base 2 will be less than or equal to 3, not more than that. If it is not found also, okay, let's try to see the found first. So now search for any number. From this search for any number, tell me which number you want to search for. 27. The answer will always be in 3. How many iterations? And as log binary search is in the center, so the more the number is at the center, the faster it will be searched for. 63 might take different time, but it will not take more than 3. It will not take more than 3. If my array size was of 10, if my array size was of 10, then now tell me the ascending order. So start from 0 and go till 9. So now how many attempts will it take max to max? 10. So one, see, it will take just one more, na? It will just take one more, because when 5 is this, so 1 ahead of 5 is 10, right? So just one extra. Are you getting what I'm trying to say? So here it was 3, it will, for 10 it will become 4, correct? Because 10 mod 2 is 5, and from 5 we know it is 3. So just one extra has been added. So if the array is of size 10 also, I will search the answer in max to max 4 steps. So if I'm searching for 99, searching for how many attempts? What happened? Did we miss out any size? 5. Okay, we gave 5 over here, no? So when we are giving the data, no need to give the size. So be smart enough, no need to give the size when the data is given. Okay, so now 99, I'll get the answer in C. Will not exceed 4, will never exceed 4. If I search for 109, getting it? Aryan, the log, time complexity of log. And for linear search, it would search at 1, then search at 18, then search at 27. So it becomes log of n. So if there were 10 numbers, it would take max to max 10 at 10 steps. So which is faster, 10 or 4? So now if I make this as 20 numbers now, then it will take max to max 5 steps. That is called time complexity of O of log n. Getting? And log n means log to the base 2, not to the base 10. Because we are splitting into half every time, right? We are splitting into half every time over here. So that's why log to the base 2. Correct? We practice these two programs, and tomorrow maybe we'll start. I'll just research the Hibernate, which Fibonacci search, right? Never.